Ever get that feeling, you're staring at your design software and it just feels restrictive.
Hmm.
Like you have this brilliant idea, this really specific vision, but the tools, they only give you these like preset options.
Yeah, I know that feeling. Or maybe you hear all the buzzwords, data, AI, and think, okay, but how does that actually help me design something?
Exactly. Well, that's what we're getting into today. We're looking at data, at code, not as these abstract techie things, but as actual materials for design.
Like a new kind of digital clay or pigment.
Precisely.
Yeah.
Something that could unlock ways of working you haven't even thought of yet.
And what's really interesting is where this deep dive comes from. It's based on a lecture, actually, called Data and Design Code for Design.
Okay.
It was originally for graduate students in architecture and urban design. But honestly, even if that's not your field, the core concepts are super relevant for anyone curious about, well, the future of design and tech.
Definitely. And the person giving the lecture, they've got a fascinating background, right? Started in architecture and urban design.
Yeah, and then moved into software engineering and now runs a design studio, NJ Studio and NJ Lab, that specifically focuses on this computational design stuff.
So they've really lived in both worlds. This isn't just theory.
Not at all. And they start with this great question, basically asking, how do you actually translate the design process into code? How can data become a design material?
And that's really the core question for us today, isn't it? It's a prompt for you, listening, to maybe think differently about how you work and what data could potentially do. So our mission here is to pull out the key insights from that lecture, give you the fundamentals of data and design without, drowning you in code snippets.
We're looking for those aha moments, maybe some surprising connections.
All right, let's dive in. First off, data in design. What are we really talking about here, according to the lecture?
Well, the lecture is quite clear. It's not just about learning software X or using algorithm Y. It's deeper.
Okay.
It's about a shift in thinking. How computation and data can become sort of woven into the fabric of the design process itself.
And this involves computational thinking. That term comes up.
Right. Computational thinking is essentially figuring out how to break down your design process, all those decisions, those steps, into a language a computer understands, which is code.
So you need the computer's language variables, functions, classes.
Exactly, the building blocks. But just as importantly, you need to understand the data you're working with, the raw material. Geometry is the key example they use.
Okay, so design data, geometry. What does that actually look like? What kind of information?
Think about the real basics. Vectors, points, lines, curves, surfaces, meshes too.
Right.
The lecture highlights vector data. That's basically homogeneous data, structured data, things like polylines or curves in your CAD software. They're classic examples.
Gotcha. The lecture also mentions raster data and lattice data. How do they fit in? Are they totally different?
Well, they look different, sure. A grid of pixels, that's raster. A structured grid of points, maybe lattice. But the lecture's point is, under the hood, it's all just numerical data. It's just different ways of organizing and interpreting numbers. Whether it's a color value or coordinates in space, it's data the computer can crunch. The interpretation is what changes.
Okay, so that's the types of data.
Yeah.
Now, how do we actually use it? The lecture talks about different cooking strategies.
Well,
Sounds interesting.
yeah, it's a nice analogy. They outline two main ways. First is the inductive approach.
Inductive.
Think of it as direct translation. You have an idea, maybe a sketch, and you write code step by step to tell the computer how to make it. Very direct, very hands-on.
That makes sense. You build it up piece by piece in code. What's the other way? The deductive one?
Deductive is more like reverse engineering. You know the outcome you want, the final result,
Right.
and then you work backwards to figure out the rule or the functions that would produce that result. Machine learning is mentioned as an example here.
How so?
Well, with ML, the system learns the connection between inputs and outputs from lots of examples. It sort of deduces the underlying rules itself rather than you explicitly programming them.
Interesting. Okay, this next bit felt really crucial in the lecture, the importance of data structures. What are they and why are they such a big deal?
Data structures are, well, ways to organize your data efficiently so you can access it, change it, work with it easily.
Right.
And the lecture really hammers this point. The ability to create data structures that truly describe your design or the problem you're tackling is key.
So it's not just knowing the code, but how to organize the information within the code.
Precisely. That's where object-oriented programming, OOP, comes in. It's a paradigm, a way of thinking that helps you structure your code and data into logical chunks, these objects that relate to each other, makes complex stuff manageable.
So the real skill isn't just syntax, it's architectural in a way, structuring the data itself.
Exactly. The lecturer says the core skill in computational design isn't just writing lines of code, it's having the experience to know which data structure best explains your design or your concept. That's the insight.
Okay, moving on, the lecture talks about discretization. Sounds
Okay.
technical. Can you break that down for us? How does it relate to design?
Right, discretization. Think
Yeah.
about the real world. It's smooth, continuous, infinite detail, right? Analog. Computers, though, they live in a digital world. Finite memory, finite processing. Discretization is the bridge. It's how you take that smooth, infinite, real-world stuff.
Like a curve or a landscape.
Exactly. And you represent it using a limited, countable set of values a computer can actually handle. It's a translation step, a crucial one.
Why crucial?
Because how you choose to discretize, how you chalk up that continuity, hugely impacts what the computer sees and what you can do with it. Get it wrong, and your results might be meaningless. It's about making that translation effectively.
And how does this connect back to things like variable types and memory limits?
Well, variable types define what kind of data you store, numbers, text, and how much memory it takes up. Discretization is how you decide, say, how many points you need to reasonably represent that complex curve without using infinite memory. You're fitting the analog world into those digital boxes.
Can you give some specific design examples? How do we see discretization in practice?
Sure. Representing a smooth curve with lots of tiny straight lines, that's discretization.
Okay.
Or a photo becoming a grid of pixels. Each pixel has a distinct color value.
Right, pixels.
Or a 3D object becoming a cloud of points. Or maybe tiny cubes called voxels. Even mapping relationships in a building, like which rooms connect using a graph structure, with nodes and edges. These are all ways to take continuous or complex spatial info and make it computable.
And the lecture emphasizes that learning how to do this translation well is a major part of computational design.
Absolutely. Figuring out the best way to discretize for your specific design problem is a core skill.
The lecture then draws a contrast between sort of normal programming cause and effect and machine learning.
Yeah.
What's the key difference there for designers?
Okay, so traditional programming is deterministic. You put in 3 plus 3, you explicitly coded the plus operation, you always get 6. Cause leads directly to a predictable effect.
Makes sense. Simple input, simple output based on clear rules.
Right. Machine learning is different. You don't always explicitly code the rules connecting input and output. Instead, you feed the system tons of examples, like here's input A, it leads to output B. Here's input C, output D. The lecturer uses the example of showing it lots of 2 plus 2 plus 4.
Okay.
From those examples, the system might infer the concept of multiplication, or addition in this case, without being explicitly told this is addition. It learns the underlying operation.
So it's less about giving direct instructions and more about showing examples and letting the system figure out the pattern.
Pretty much. And this links back to the idea that computational design, especially with ML, is about finding good ways to describe design problems so computers can learn from them, not just follow rigid steps.
Which leads nicely into the next bit. Analytical versus generative AI in design. What's the distinction?
So generative AI is what gets a lot of hype AI that creates new stuff. New images, new text, maybe new design options based on its training data?
Like Mid-Journey generating images or suggesting floor plans?
Kind of, yeah. Analytical AI, though, is more focused on analyzing existing data, finding patterns, making inferences, predicting outcomes.
And how does that apply to design?
Think about analyzing a building design for energy performance, or predicting structural stress points, or optimizing material usage based on site data. That's analytical AI territory.
And the lecturer had a take on which is more immediately useful for designers now.
Yes, the view presented was that analytical models are probably more crucial for practical design work right now. While generative AI is exciting and has huge potential, analytical AI offers more concrete tools for solving real-world design problems today, making data-informed decisions.
Okay, so how does all this The data, the code, the AI connect back to the actual design process, the iteration, trying things out, finding better solutions.
Well, once you have these computational skills, you can approach iteration differently. Instead of just manually tweaking a design, you can define parameters, set up rules.
And let the computer explore variation.
Exactly. You can test way more possibilities much faster, much more systematically, and that links to optimization.
Right, optimization, finding the best solution.
Kind of. It's about defining a specific goal, maybe maximizing rental income for a building design or minimizing construction waste.
Okay.
And then using computational methods to find the design variation that performs best according to that specific target within whatever constraints you set.
The lecture also sketched out a learning path, didn't it? From the very basics upwards.
Yeah, the idea is you start with fundamentals understanding data types, basic coding logic, then you move towards visualization, 2D, 3D. And eventually, you're building actual design tools or solutions.
And even simple stuff can be valuable.
Absolutely. The lecture stressed that even coding a simple version of a known design algorithm can teach you a ton about how it works. And these skills aren't just tied to one platform. They could potentially be applied to web tools, apps, whatever.
Let's talk about the why now. Why should designers bother with all this?
Yeah.
The lecture used a really strong analogy about materials.
Right, the material innovation analogy. Think about how glass, steel, concrete revolutionized architecture. They opened up totally new ways to build, new forms, new possibilities.
Things that were unimaginable before those materials existed.
Exactly. The argument is that data is like that. It's the powerful new material of our time, offering a whole new dimension for design exploration and creation.
And this ties into ideas about accelerating change, Kurzweil, and exponential growth.
Yeah, the lecture touches on that. The idea that technological progress isn't linear, it's speeding up. So our current grasp of what's possible with data and computation might be just scratching the surface. Think about smart cities, AI, machine learning. They're all fueled by data. How we collect it, process it, use it, it's becoming central.
But what about the argument that this isn't real design?
Yeah.
That it's too technical, not creative enough?
The lecture tackles that. The point isn't that computation replaces design intuition or creativity. It's a new methodology, a new set of tools that expands what's possible for the designer. It offers new avenues, new ways to express that creativity.
Then there was this concept, data as compressed phenomena. What's that about?
It's a way of thinking about what data is. Essentially, it's a shorthand, a compressed representation of something complex in the real world.
Like statistics capturing social trends or sensor readings capturing environmental conditions.
Exactly. It's taking messy reality and turning it into structured information. And understanding different data types, numerical, categorical, discrete, continuous, helps us work with these compressed representations effectively.
Okay, like taking a whole city block and representing it as data points, building heights, materials, occupancy.
Right. That compressed data lets you analyze patterns, see things you couldn't see just by looking, and then make more informed design choices based on that insight.
This leads to another really interesting idea. Software as executable knowledge. Can you unpack that one?
Sure. The lecture mentioned Andrej Karpathy's Software 2.0 idea, where software increasingly learns from data rather than just being explicitly programmed, which is Software 1.0.
Okay.
But the bigger point is seeing software itself as the way we cook data, the way we make it useful. It's like all the accumulated knowledge, the algorithms, the techniques developed over years, decades.
It gets baked into the software.
Exactly. It's knowledge in an executable form. When you run software, you're not just running code, you're running generations of human insight and problem solving.
That's a powerful idea. So it's different from knowledge in a book, which is static.
Right. Software makes knowledge actionable. And even simple design tools are doing incredibly complex math and logic behind the scenes. Understanding the basics, like code, gives you more leverage, more control over that power.
Which ties into the next anecdote. Conquering software, not being conquered by it. What's the lesson there for designers?
It's about the learning curve with software. You start basic, maybe move to more advanced tools, but the warning is not to just skim the surface.
Don't just learn the buttons.
Pretty much. The advice is to really master a tool. Understand its logic, its limits. Why does it work the way it does?
I remember feeling that way with 3D modeling at first, just pushing shapes around.
Right. Until you grasp the underlying geometry, how the software actually thinks about those shapes, you're kind of limited by its presets.
So deep understanding gives you freedom.
Exactly. Freedom and choice. Coding is presented as part of that understanding. The fundamentals lets you use any tool more effectively, more expressively, rather than being dictated by it.
The lecture then shifts perspective a bit, talking about a competitive edge through uniqueness, not just competition. What's the angle there?
It's suggesting a move away from just trying to be better than others at the same things. Instead, focus on what makes you different.
Cultivating a unique niche.
Yeah. In a field with lots of experts, maybe having this computational skill set, this different way of approaching problems, is how you stand out. It's about adding a unique value, not just competing on the same terms.
Computational design can seem like this impenetrable black box sometimes.
Yeah.
How does the lecture try to demystify it?
By breaking it down, it emphasizes looking at the entire design process A to Z and identifying all the small decisions, the steps involved.
Making the process explicit.
Exactly. Quantifying things where you can, qualifying things where you need to, making the problem understandable in a way that computation can actually engage with it. It's not magic. It's about making design thinking more structured, more translatable.
There's also a cautionary tale about the easy software trap. What's
Yeah.
the advice there?
It echoes the earlier point about mastering tools. The anecdote is about tutoring, seeing people jump from one software to the next, more complex one, without ever really learning the first one deeply.
Been there.
Haha, yeah. The advice is pick one tool and really dig in. Understand its guts. Why are the menus laid out that way? What's happening computationally when you click that button?
Mentally visualize it almost.
Right. That deep understanding unlocks so much more potential. And it helps you talk to developers, collaborate better, because you understand the underlying mechanics.
Okay, so wrapping up the core arguments. Why, ultimately, does the lecture argue that designers need to get comfortable with code?
It pulls together all those threads. Code helps you create custom animations or visualizations. It lets you build quality checks for your models. It enables deeper experimentation. It helps you solve very specific design problems precisely.
So it's a tool for precision, for exploration, for quality.
Yes. But the fundamental idea driving it all is coding is how you interpret your design process into this powerful new material, data. It's about harnessing that potential.
So bringing our own deep dive towards a close now, what's the big takeaway message from digging into this lecture?
I think the main thing is that understanding data and code isn't just about adding a technical skill. It's about gaining a whole new lens, a new perspective on design itself.
Moving beyond just intuition.
Yeah, moving towards a collaboration, a partnership between your design thinking and the power of data and computation. And that collaboration can open up genuinely new creative territory.
It's a compelling vision. And that leaves us with our final thought for you, the listener. In this world that's becoming so driven by data, how might your understanding of computation reshape your own design practice? What unique things could you unlock by really treating data as a fundamental design material?
It's definitely something to mull over. And if this has piqued your interest, the lecture materials, the website, the book mentions seem like a great next step for continuing that exploration. There's clearly a lot more depth there.
Indeed, lots to think about.